Welcome to the fourth session, the fourth press conference at this EGU assembly. The topic will be sea level changes and their impacts in coastal oceans. The speakers are Anny Cazenave, and she's from France, Svetlana Jevrejeva from the UK, and David Vaughan, also from the UK. So I would say good luck.
Thank you. So,
Svetlana.
No, Anny. Okay, I will start with just a very brief introduction. So first we apologize because we did not prepare anything except Svetlana, because we had no instruction. But anyway, so very brief introduction about sea level rise and what do we know? For about 2 decades, we observed the global mean sea level evolution with satellite, altimeter satellite. And with the satellite, we measure the rate of rise larger than 3 millimeter per year, exactly 3.3 millimeter per year, which is about twice faster than the rate which was recorded by tide gauge during the last century, or I would say the last 50 years. Maybe Svetlana will talk about that. I don't know. You will talk many on the future. Anyway, so it's what we measure. We know that on time scale from a few years to a few decades, the two main contributions to sea level rise are thermal expansion due to ocean warming, and we know that the ocean have been warming during the last 50 years. We know that from in situ temperature measurement, and the second main contribution is from land ice melt, glaciers melting and the ice sheets. And David will talk about, I suspect, from land ice melt. So, what are the respective contribution of these two factors? I would like to recall that in the IPCC report published in 2007, the sea level budget was computed for the decade 1993 to 2003. And for this period, it was shown that about 50% of the rate of sea level rise was due to ocean warming, that is thermal expansion, and the other 50% was due to land ice melt. But since then, that is since about 2003, what do we observe? We observe that thermal expansion has made a pause. We don't know exactly the cause of this pause, but the rate of thermal expansion since 2003 was much less than the previous decade. So the contribution to sea level rise was very low since 2003. But what is interesting is that sea level continued to rise at about the same rate as the previous decade. And from independent observation, from glaciers and ice sheet mass balance, it has been observed that we I don't know how to say that, we face an acceleration of the land ice melt. So that, in fact, land ice melt took over the ocean warming, and the result is that sea level has continued to rise at the same rate. So this is the observation. I will stop here because my colleagues will talk in more detail. I think on the probably I don't know who starts. Probably David, about the ice sheet contribution and this very curious observation of ice mass loss acceleration and what will be the future of that. And Svetlana will also talk about future sea level projection, I think. Mm-hmm. Okay, so I stop, and if you have questions, I will be happy to answer later on.
Good afternoon, good day. I don't have for you a really strong new science story, and what I will be talking about tomorrow at our session will be really about the framework that we'll be needing to use to make stronger predictions about sea level rise in the future. We have a current rate of sea level rise that is somewhere between 3 and 4 millimetres per year, and that's not going down, and it won't go down in the future. It will continue to rise, and the question is whether it will continue at about that rate or whether it will accelerate. And for the next century, we might be looking at sea level rise that, at that rate would be about 30 centimetres by the end of the century. But if it accelerates, we might be looking at sea level rise globally of up to a metre. Now, there has been a great deal of discussion about even bigger numbers than that within the science community, very low likelihood but high impact events that could cause sea level to rise more than that. I think what we're interested in here, and the EGU conference in Vienna brings together some of the best minds working in this field, is really trying to understand the most likely rates of sea level rise for the future as a basis for society's endeavours to protect ourselves against it. Sea level rise actually impacts the global climate debate in two different ways. The first is that sea level rise it's a one-way street. It's going up at the moment, and there's no reason to believe that it will not keep going up in the future. And we must adapt to that sea level rise. We must protect our coastal cities. We must in place practices that protect people living in coastal areas. The other way that sea level rise impacts the climate change debate is in terms of the legacy that it provides, the legacy that it implies for future generations. Once sea level rise begins through the loss of the major ice sheets of Greenland and Antarctica, then it may continue for many hundreds of years. Even after the emissions of carbon dioxide and methane, the greenhouse gases, have stabilised, sea level will continue to rise. And that's potentially a very long legacy for future generations to deal with. So I think there's two very clear timescales on which we need to make our predictions. One is this really the horizon for society to do its adaptation planning, which is really 100 to 200 years. In the UK, there are issues around the replacement of Thames Barrier, which have a timescale of certainly more than 100 years, perhaps 150 years of planning horizon. So we need to be looking that far away as scientists. In other countries, perhaps the timescale for planning is even higher than that. The Netherlands perhaps wants 200-year predictions. So scientists are actually faced with a very difficult task. We're trying to do something that scientists have traditionally always shied away from, which is to make predictions about something that's going to happen in the future that's actually very hard for us to test. As scientists, we're very reluctant to do things that are untestable. So in a sense, what we're attempting to do is to build a framework for bringing on new tools, new methods of science that will allow us to make projections that we are happy with, that we can be confident in for the next couple of 100 years. And there are several initiatives that are being exposed for the first time at the EGU that are really helping us move along that way. The first is that we have the recent launch of Cryosat-2, the satellite that will measure mass changes in the ice sheets of Antarctica and Greenland, and also sea ice, although that's not a sea level issue. We have a new effort called Ice to Sea, which is a European-funded programme involving 24 institutes across Europe, which will deliver sea level rise projections for the next IPCC report. I'm the coordinator of that, so I can answer questions on that. We have the first presentations about ice to sea, scientific presentations at this meeting. We don't have our projections to give you at this stage, but in maybe next year or the year after, when we come back, I'll be delivering those projections. But ice to sea is building new models of ice sheets. We're collecting data that shows how ice sheets in Antarctica and Greenland are currently retreating. And we're stimulating a lot of new, fresh minds, young people, young scientists who are beginning their careers and really will be the bedrock for future projections and the policy debate in future. So that's really all I've got to say at this stage. Thank you. Svetlana.
Right, good afternoon. So I work for Proudman Oceanographic Laboratory in Liverpool, and I think it's very exciting time. Everybody has a lot of interest about sea level, and I will show just some example. I will have talk tomorrow during our session, and I'm sure there will be most probably more interesting and better talks, but I have just few slides to show our results. And the title, of course, it's a simplified title. For my talk, I have different title. It's Volcanoes and Sun will not hold greenhouse-driven sea level rise this century, in mid-21st century. What we did, it was a simple exercise using statistical model, and we look for the relationship between radiative forcing for the past 1,000 years and observe sea level rise from tide gauges for the past 300 years. And on the base of that relation, we assume that if we have quite good model and we could reproduce 1,000 years back, so we could maybe be ambitious and try to see what happened with sea level rise for the next 100 years using 6 IPCC scenario of radiative forcing. And so my first slide, it's our result of sea level projection for A1B scenario. It's not extreme scenario, and I'm not trying to bring any news. So it's nothing new. So statistical models show much higher numbers, and this is something like the sea level rise with A1B scenario will be in a central number, like up to 1 meter. And you see that it's huge confidence interval up to 1.4 or from 60 centimeters. And if you compare with old numbers from IPCC report 2007. But I think the most interesting things which we try to do in our study, and which is quite new. So the previous slide, radiative forcing here, it's mostly driven by CO2 increase. In all these 6 IPCC scenarios for future, there is no contribution from volcanic eruptions or solar irradiance. So we introduced some alternative scenarios for volcanic forcing and what could happen with solar irradiance. We took volcanic forcing from the past. During 13th century, it was very intensive volcanic eruptions. So we just cut this forcing from 13th century and assume that the same happened in 21st century. And the result is a red line. So the black line, it's what would happen with sea level under A1B scenario. So as I mentioned, it's something like 90 centimeters sea level rise. So if A1B scenario will be combined with volcanic forcing for the 13th century, we will have red curve. So previously, volcanic forcing lowered sea level quite effectively. So in future, even if we will have natural disasters, so we will lower sea level only by 10 centimeters, 10, 15 centimeters. Then we created artificial scenario, like, for example, we have every 4-year Pinatubo eruption, like it used to be in 1992. So that blue line, what happened with sea level if we have such massive eruption like Pinatubo So generally, we are buying only about 20 years here, if you look at the results. So we still will have substantial sea level rise, even with volcanic eruption, and it will get the same stage as without any natural forcing in 20 years' time. And the same, you can see it's only about 15 centimeters lowering. And we look as well in different contribution, what happened if solar variability will be in lower stage. And in general, the conclusion that there is no mercy from nature. It will, no natural disasters would significantly lower sea level. And I think we have seriously think about how to reduce CO2 emissions. And that's it. And this just, if you would like to contact, I have co-authors. And this paper published, I think a few weeks ago. And tomorrow I will have a talk in our sea level session.
All right, thank you very much. Are there any questions?
Svetlana, could I just start? Why is that? Why is there no slowing or no reasonable slowing from these events? Is that because we're already committed to thermal expansion of the oceans for the amount of heat that we've put in there? What are the reasons why it will continue to go up even with those events?
Well, the first, of course, you're absolutely right. We already committed, and sea level is rising and accelerating, and whatever we do, even if we stop now emissions and forcing will be zero, the sea level rise will be still up to 20-30 centimeters at the end of 21st century. But why there is no substantial contribution from volcanic eruption? We still have the same lowering effect, but it's just because the radiative forcing due to increase in CO2 is just huge. So it's not, we're increasing radiative forcing 6-8 times compared with previous centuries. And we have the same effect from natural forcing, or about the same. I shouldn't say the same, but similar. But just contribution from greenhouse gases is much higher during 21st century that we observe or experience in 20th century.
More questions?
David, what's that? David, my name is Kuren Giamaya from Nature. What's that new European Union funded program called Ice to Sea?
Ice to Sea.
Is
so
this an
ice
acronym? Or?
To, like the digit, and then sea.
Okay.
And there is a website, www.icetosea.eu.
And is it a very new program?
Yeah, so this is a new Framework 7 program that, as I say, has 24 partners, institution around, well, mostly in Europe. It has actually been running now for just over a year. But I will be honest and say we haven't made a big press statement about our starting because I'm not particularly keen on promoting a project that hasn't produced results. So there is now the first steps in the program are being begun. I can tell you basically what our program does. It's the first time that we will actually take emission scenarios of carbon dioxide and methane to produce global climate projections for the next 200 years. And then we will use those global climate projections to produce specific regional climate projections for Antarctica, Greenland, and also alpine glacier systems, mostly Antarctica and Greenland. And then we will drive a new suite of ice sheet and glacier models to predict the cryospheric contribution of sea level rise. So that's actually, there's 3 specific stages in that process, from the global climate projections, regional climate projections, and actually ocean projections, to the final projections of how the ice will be lost. So it's a big undertaking for us, and it's also scheduling it is the biggest task. We have to produce results that will be available for the next IPCC assessment, which will close its doors to new science in mid-2012. So we have to do each of those tasks by then. And we've already done the first part of that. We've run the global climate models for 200 years, and those have been passed around the science community to begin the regionalisation of those global climate models. So that's work that's been done by the Hadley Centre. It's been discussed at this conference by Jamie Ray, and that's our first stage on the way, if you like. I guess the reason why we are doing this is that we believe that the biggest uncertainty in sea level rise, not necessarily the biggest contribution, but the biggest uncertainty in sea level rise is in how the ice sheets will change. They have the capacity to to produce sea level rise that's substantially more than thermal expansion of the oceans, although thermal expansion is at the moment the biggest single contribution. So is there? Sorry.
Not for the few years.
Sorry.
Not for the last few years.
Okay.
Okay,
yeah,
but
Antarctica and Greenland are separate contributions, and glaciers. But yeah.
Annie, can we just talk about the pause?
About
the pause in thermal
the
expansion?
pause, yes.
Yeah. And because I think the oceans are still warming, are they not? Do the buoys show that the oceans are still warming?
No, because in fact, thermal expansion and ocean heat content is they show the same behavior, and we have seen this a steep rise since 1993. And then since 2003, some flattening, but it seems that with the very recent data from Argo, the rise is starting again. At this moment, we don't know what is the cause, but we say it's natural variability, probably redistribution of heat inside the ocean. Why exactly, we don't know, but maybe during this meeting we will have new information. I hope so. So it's not exceptional, because if we look at the thermal expansion evolution since 1950, it's not a monotonic rise, it's something like that, and so it does not seem to be exceptional. What is, I don't know, maybe not interesting, but is that during this this pause, the land ice contribution has increased considerably. So if this continue in the future, and if ocean warming start again, maybe we will see some acceleration in sea level. We don't know, but it's what we observe. So we have still a lot of work to do to understand this respective contribution and their interannual variability and so on.
How long does that take to appear in the JSON data?
There is no delay in the response, because there is two different things. When you have temperature anomaly measurement at every location over the ocean and different depths, you can measure the contribution to sea level, and this is what the satellites see, and there is no delay in the response. The other point is, what is the history, the past history of a particular temperature anomaly, which is measured at a given location and given depths, and that we don't know. We have also to work on that to understand how heat is transported by the circulation from, laterally and from the surface to the deep ocean. And here again, this is work underway, and we don't have still a clear picture. I'm not sure I am very clear, but okay, no. I would like, up to now we have talked about the various contributions in the global mean sea level. But what we have observed with satellite altimetry is that sea level rise is not uniform. You know that, probably. And in some region, the rate of sea level rise has been 3 times faster than the global mean. We know now that it is mostly due to non-uniform ocean warming. Why is it so? I mean, why the Western Pacific is rising faster or warming faster also? You can say that than other region. It's precisely linked to the past history of temperature anomaly, but this has to be studied. But anyway, and we expect that in the future, sea level rise will not be uniform either. So for impacts, this is in fact very important.
Sorry, can I ask? I'm sorry.
Have there been any studies done on heat flux in the world's oceans, though, recently?
On what?
Heat flux.
What do you mean exactly?
No, just how, for example, heat is being transported.
Yes, no, it's. My answer is no. There is no clear picture of how heat is transported. How heat is transferred from the atmosphere to the upper ocean, and then how it is transported to the deep ocean by the circulation. So there is no clear picture of that so far. I hope in the future people. I'm sure that people are working on that topic, which is very important. Okay. But
no, it seems like a key ingredient.
Yes, absolutely. And it is important also for projection, because so far climate models are roughly unable to predict this regional variability. Unfortunately.
It's always very interesting when you come to a press conference like this, the scientists in a room, we always discuss what we don't know. I mean, that's what we do, and that's what we're supposed to do, is focus on the next thing that we're going to answer. So we always focus on the uncertainties. And actually we lose sight sometimes of the progress that's being made. And a meeting like this is actually a very interesting time, because it's lots of little building blocks that come and build the story. And you go away and you think, actually, we really have made some progress here. And it's not maybe just one big talk that said, now we know this. Yes, lots of little things that add up. And I was thinking back, and I was thinking, if you asked me 10 years ago, well, is Antarctica losing mass to the ocean, or is it gaining mass? I couldn't have told you with any confidence. You asked me, was Greenland losing mass or gaining mass? I wouldn't have told you. Is the oceans getting higher? Is sea level getting higher at a measurable rate? Well, and now those three questions we can answer with a degree of precision, and we know the regional patterns across Antarctica, across Greenland, across the world's oceans. We know where to go and look to get the next stage in the story. And all of these, things come almost as a process of attrition, of small bits of information being put together. And it's this kind of meeting where actually everybody gets together and shares those little tiny building blocks that we actually really make progress as a community. So, it's a way I think of looking at it, that we look for the big story. When we talk about what we don't know, but we are actually making some progress.
I would like to, may I add a short comment to that? I think it's true. Two decades ago, we knew very little. But the main progress is due to availability of observing systems from space and in situ. Because now we have this series of high accuracy altimeter satellites, top 8, JSON 1, JSON 2, JSON 3 has been recently decided, and this is very important for monitoring how sea level is changing. We have all the remote sensing data to look at the ice sheets, altimetry, ISAT, laser and radar altimetry, INSAR, the GRACE satellite, which are very important. Space gravimetry is a very important tool for measuring the ice sheet, but also for looking at the change in ocean mass, which is one of the two components of sea level rise. GRACE does everything. It even is very useful to look at earthquakes, but anyway. And we have the Argo system, the profiling floats which measure ocean temperature and salinity. And without all this observing system, we would not be able to say anything on sea level, or very, very little, I think. And it is very important that this observing system continue in the future. I mean, perennity of observation is essential.
I will just add how important tide gauges.
Oh yes, tide gauge, of course, important, yes, because they are the historical. They offer the historical information, but
yeah. So if we go back and we try to understand past variability or why sea level started to rise 200 years ago or something, we still rely mostly on tide gauge observations, and I think they will be for a very long time still like benchmark for satellite missions and other new techniques to measure sea level variability and sea level rise.
All right. Do you have any more questions? Anyone? No? Oh, you do. Yeah.
This is for David Vaughan. What exactly is the state of the Antarctic ice sheet as far as mass loss outside of the Antarctic Peninsula, of course?
The mass loss from the Antarctic ice sheet is now, we can see that it's isolated in about 2 or 3 substantial areas. And each of those areas appears to be one where the ocean is coming into contact with the ice sheet. So we believe that it's strongly affected by the oceans. The Amundsen Sea embayment is the area that's the biggest red dot on the map, if you like. And that's an area where we've recently published assessments from the IceSat NASA satellite to show that there's a substantial wasting of the ice across an area about the size of Texas. It's a big area, but the thickness change averaged over that area is a few centimetres per year. It's not really about either the area or the current rate of loss of ice from that area. It's about how rapidly it's changing, and we have evidence building up from in situ GPS measurements on the ground. I can point you to papers that have just been published that show the glaciers in those areas are accelerating. The ice sheet is thinning in that area, and where it begins to float is moving inland. And so those 3 interacting effects of the ice sheet, speeding up, thinning, and starting to float further inland, are really the things that concern us, and we need to know how that's going to accelerate in the future. So, I mean, if you want to talk numbers about sea level rise, then the Amundsen Sea embayment is contributing probably at about 1/3 of a millimetre of sea level rise at the moment per year. But the rate at which it's accelerating at the moment means that probably, certainly before 2020, it will be 0.5 millimetre of sea level rise per year, coming out of that one set of glaciers alone. And it could continue over the next decades and amount to even more than that. One of the things I'll be talking about tomorrow is really whether we can try and think about how to imagine what the limits on that system are, the limits to the rate at which we can lose ice from that system. But I don't have any strong science conclusions to give you on that at the moment.
Last
that
question from someone?
Yeah.
Okay. Yeah, you?
Yeah, just to pick up what you were saying about the gravity satellites. I mean, there is mass distribution. I mean, the water moves, doesn't it? And obviously that affects sea level as well. And I think there was some data that showed that the Arctic ocean basin was going down for a while. Certainly in the 90s, that was evident in Envisat data. I think in ERS data. So, I mean, can these polar regions, as they melt, does that have any impact on where the water goes?
Yes, absolutely. You want to answer that?
I can
Yes,
answer
absolutely.
that. Yes, for Europe, the difference between Antarctica producing sea level rise and Greenland producing sea level rise is known. If we lose a particular mass of water from Antarctica, it will cause more sea level rise in the northern hemisphere than if we lose the same amount of ice from Greenland. And that's because there is this change in the shape of the sea surface around the world due to the gravitational influence. It's a second order effect, and that's the point. I mean, if we raise sea level by taking ice out of Antarctica or Greenland, we still get global sea level rise, and there's a second order effect that means there's slightly more, let's say, in the northern hemisphere if we lose it in Antarctica. And we're beginning to understand now how to make those predictions. And for ice to sea, when we come back and give you our final predictions, there will be some element of that regionalisation that we will give you. However, there are other effects that are actually going potentially to be quite dominant in the long-term future about changes in ocean circulation, and change in regional temperature of the seas and coastal waters that actually could have substantial local impacts. So we talk a lot about global sea level rise, but as with global climate change, where you're living isn't always the mean of
Yes.
change across the world. So we have to worry about that in future. But first, we've got to get the global sea level rise sorted out, and that's, I think, the task for the next few years up to the next IPCC report.
Yes, no, I agree. There are several factors causing regional variability. We talk about thermal expansion, which is really the dominant, but the redistribution of mass due to ongoing land ice melt is another. You talk about circulation change, and we have to understand all these effects. And this is why sea level studies are so complicated. They are totally cross-disciplinary. They involve, as you know, oceanography, glaciology, solid earth processes, hydrology. We did not talk about land hydrology, but this is another contribution to. Presently, it's small, but it could change in the future. So this is very interesting, but very challenging because it's so many different disciplines which are involved in sea level.
All right. I would like to thank you all very much. And if you would like to go to the session, it's tomorrow morning from 8:30, room D.
Okay.
Okay.
Thank you.
Thank you for your time.